You know, for as long as we've built cities, we've had this deep-seated fear of the ground just giving way. Earthquakes are one of nature's most terrifying forces, mainly because they seem to strike out of absolutely nowhere. But what if they don't? What if the warnings are there, and we've just been looking in completely the wrong place? Okay, let's get into this.
I mean, this is it, right? This is the billion-dollar question that has kept geophysicists up at night for centuries. If we could reliably say yes to this, it would change everything. It could save countless lives and totally reshape how we prepare for disasters. The stakes just couldn't be higher.
And for the longest time, the answer has been a pretty firm no. I mean, we've tried everything, from monitoring tiny seismic waves to, yes, even studying weird animal behavior. But so far, nothing has ever been a reliable predictor. The general consensus in science has always been that short-term earthquake prediction is basically impossible.
But here's a thought. What if instead of putting our ears to the ground, we should have been looking up, like way up, at the sky? There's this fascinating and, kind of controversial theory that suggests the clues to a monster quake might actually be broadcast into our atmosphere days or even weeks before the shaking ever starts.
So our journey here actually starts deep, deep underground. Just try to imagine the unbelievable forces building up before a major earthquake. You've got tectonic plates grinding against each other with a pressure that's just mind-boggling. And all that stress doesn't just store up energy. It can actually squeeze out a hidden messenger.
And that messenger is a gas called radon. Now, radon is a radioactive gas that's pretty much everywhere all the time. But usually it's locked away safely in the rocks deep beneath our feet. So think of it like a silent whistleblower, just hanging out in the Earth's crust. Under normal conditions, it stays put. But when the pressure is on, the theory goes that all that pre-earthquake stress creates tiny little cracks in the rock. And these cracks act like escape vents, allowing radon gas to seep up into the atmosphere in much, much higher amounts than usual. We're not talking about a tiny leak here. We're talking about a significant spike. A potential first alert.
Okay, so a little extra gas escapes from the ground. Big deal, right? Well, this is where things get really wild. This is where a massive chain reaction kicks off. That release of radon, that's just the very first domino to fall in a cascade of events that travels all the way up from the ground through the atmosphere and right to the edge of space. Scientists call it the lithosphere-atmosphere-ionosphere coupling model, or LAIC for short, and this lays it out perfectly. First, radon gets released. Because it's radioactive, it zaps the air around it, creating charged particles, or ions. These new ions are like little magnets for water vapor, causing them to clump together. This clumping can create a visible haze, and, get this, it releases a bunch of heat, something our satellites can actually see. And if the conditions are just right, it can even form clouds. Yep, you heard me right. The theory proposes that a gas seeping from the ground can literally trigger the formation of actual clouds in the sky. I know, it sounds like something straight out of a sci-fi movie, but some of the observations are just really hard to ignore.
I mean, look at this. Researchers have actually documented these bizarre, long, thin clouds that seem to appear directly over active fault lines in the days leading up to an earthquake. Now, I have to say, this is still highly debated in the scientific community, but it's a pretty stunning piece of potential evidence. It really suggests this atmospheric domino effect might be leaving a trail that we can actually see with our own eyes. Okay, so we've got a signal that traveled from the crust all the way up into the atmosphere. But believe it or not, the story doesn't end there. It turns out our entire planet has a natural background rhythm, a kind of planetary heartbeat that we might be able to listen to for signs of distress.
These are called the Schumann resonances. So basically, the space between the ground and the ionosphere acts like a giant natural echo chamber. And all the lightning strikes happening around the world all the time are constantly making it ring like a bell, but at a very specific, super low frequency. It's literally the planet's natural hum.
This planetary heartbeat has a main frequency of 7.83 hertz, a rhythm so low we could never hear it. And then it has these little echoes at higher frequencies. Just think of it as the constant baseline electrical rhythm for the entire globe. And this is where it gets a little bit mind-bending. The Earth's fundamental frequency of 7.83 hertz, it falls right smack in the middle of our own alpha brainwaves, the ones that are associated with being calm and meditative. It's a really fascinating, though maybe speculative connection between the planet's rhythm and our own.
So here's the big connection. If that pre-earthquake process is powerful enough to change the atmosphere and ionosphere in one location, could it be powerful enough to mess with this global electrical circuit? The idea is that the LAAC process could create a sort of disturbance in the force, causing a detectable flutter in the Earth's heartbeat, a cosmic arrhythmia.
Okay, let's just pause for a second. This is a spectacular story, right? A signal that starts with stressed out rocks, creates weird clouds, and then alters the entire planet's heartbeat. It's compelling, it's elegant, but does any of it actually work? It's time to switch gears from theory to the hard, cold data.
Because at the end of the day, that is all that really matters. Can we turn all these fascinating ideas into a tool that can actually forecast earthquakes? Well, to answer that, scientists recently turned to the most powerful pattern finder on the planet, machine learning. A massive study looked at 38 years of data from over 100 monitoring stations all over the globe. They fed all this info into a machine learning model and basically asked it, can you tell the difference between a normal day and a pre-earthquake day just by looking at the ionosphere? The result? The best model scored a 71% on what's called a weighted F1 score. Now that's just a fancy way of saying it's pretty good at both being right and not missing real events. And 71% is way, way better than just random guessing. So, a 71% success rate sounds pretty incredible. But, like with any truly groundbreaking science, you gotta look closer. This number is definitely a promising signal, but it is not the whole story. The researchers themselves were really clear about the limitations here.
And this really highlights the challenge. The model's performance changed a lot depending on how they tested it. For instance, a model trained on data from Japan didn't do so well trying to predict quakes in California. That suggests there isn't some universal one-size-fits-all signal. So the big takeaway is this. While there is definitely something going on up there, using it as a standalone prediction tool, that's still a big question mark.
So where does all this leave us? Are we just back at square one? No, not at all. This research has opened up an absolutely incredible new frontier. But it also teaches us a really valuable lesson about just how complex this problem is. So no, the LAIC model and looking for weird clouds isn't the magic answer we were all hoping for. There isn't one single earthquake cloud or one specific ionospheric flutter that's going to tell us exactly when and where the big one will hit. But it might be one of the most important pieces of the puzzle that we have ever found. The future of earthquake forecasting probably won't rely on just one signal, but on many. Imagine a system that combines the traditional seismic data with real-time radon gas detectors, satellite thermal cameras, and this new ionospheric monitoring. By layering all of these different clues on top of each other, a much clearer picture might just start to emerge from all that noise.
We may not be able to predict earthquakes by just listening to the sky alone, but this research forces us to ask a much more powerful and much more hopeful question. We now know the Earth whispers its secrets in so many different languages, through the ground, through the air, and through the very edge of space. So, what happens when we finally learn to become fluent in all of them?